Alrighty, in this video we are going to be talking about more on parametric derivatives. This time we're going to do applications on it with writing tangent line equations. Now we know that the derivative of y with respect to x is dy dx, but with parametric equations that's going to be dy dt over dx dt. Two important things to note. We have a horizontal tangent line when dy dt is equal to 0, aka whenever the numerator is equal to 0, given that dx dt can't be 0. And remember, that's because we do not like 0 over 0. Same thing here, we have a vertical tangent line whenever the denominator is equal to 0, so dx dt is equal to 0, and given that dy dt can't be 0. We'll probably look more into that whenever we do number 3 there. All right, so for number 1 and number 2, what we're going to do is write the equation of the tangent line. Here for number 1, we have t is equal to -1 for the parametric equations. X is equal to 1 over t, and then y is equal to t. Now, the goal of this, of course, is to not eliminate the parameter and just use this right here, right? So we have that. Now, obviously, if you guys were to think about this one is an easy one for us to eliminate the parameter because y is equal to t. So then we can say x is equal to 1 over y, and then y is going to be equal to 1 over x. And we're going to see a visual diagram of this whenever I show this to you guys on Desmos. But for the sake of this lesson and for the sake of something like number 2, we are going to put everything in parametric so that we could actually do it without having to eliminate the parameter. Now, in order to do that, I need to figure out what my rectangular equation is, because whenever I'm writing the equation of a tangent line, I always want it so that it's in terms of a rectangular equation. Okay, so in this case, I'm going to plug in -1 so that this becomes -1, -1 in terms of my rectangular coordinate. Once I get my rectangular coordinate, I just need to figure out what the slope is. And remember, the slope is just going to be dy dt over dx dt. Now, whenever you are taking the derivative of this, please do not take the derivative all at once like this right here, okay? Please, just like L'Hopital's, please give me the derivative of dy dt. Or give me dy dt and give me dx dt. So we know that dy dt is just going to be 1, and we know that dx dt is going to be -1 over t squared. Then you could figure out what dy dx is, because that's going to be 1 over -1 over t squared, or -t squared. dy dx at t is equal to -1 gives us -1 squared, or -1. Which gives us our tangent line equation to be y plus 1 is equal to -1 x plus 1. That is my tangent line equation. All right, so here's what we're going to do. I am going to put this on Desmos so that you guys can visually see it. This one's 1 over t. 1 over t, comma t. And once you do that, we get this lovely parametric equation right here. We did see that t was equal to -1, so I'm going to move this so that's like -3 to 3. And you can see that, actually let's do 9, so that you can actually see it, -9 is 9. And you can see that, hey, it looks like our reciprocal function of 1 over x, or 1 over t. Specifically at time, or t is equal to -1 here, we know that our tangent line equation is y is equal to 1, -1, x plus 1, which is right there. And if I were to do this to be -1.8 and 0.8 or something like that, you could see, why did I do that? -1.1. Then -0.9. Can't really see it there, but you can see that, hey, that's my tangent line equation right there. Very cool. We're going to do the same thing for number 2, where t is equal to pi over 4, and we have the parametric equations of sine t, and then cosine t. Now, this one is another one where theoretically you should know what the equation looks like, because this is just a circle. And I could say negative 2 pi to 2 pi. It's just your circle. Of course, remember that the goal of this lesson is to not try and eliminate the parameter and do it with the parametric equations. So in this case, what we're going to do here is figure out what dy dt is, and that's just going to be negative sine of t. Figure out what dx dt is, that's going to be cosine of t. Figure out what dy dx is in terms of t being pi over 4. So that's negative sine pi over 4, cosine pi over 4. Lucky for us, pi over 4 is root 2 over 2 for both of them, which means that our derivative, our slope, is negative 1. Now, I forgot to give you guys the rectangular coordinate, but if you plug in pi over 4 into sine of t and cosine of t, like I said, you'll get root 2 over 2, root 2 over 2. And then if I were to do this, pi over 4 is like, I can't draw this because I'm not on my notability, but we should know that the tangent line is going to be negative. Is equal to negative 1 x minus root 2 over 2. There you go. Very cool. I know. Now, of course, you're not going to see simple, easy peasy equations or problems like number 1 and number 2, where theoretically, yes, you can eliminate the parameter, but please don't. That's just more work. Now, something like this is a little bit crazy because we want to find the horizontal and vertical tangents for the parametric equations. X is equal to t squared minus t plus 2, and y is equal to t cubed minus 3t. So what I'm going to do here is probably look at what this is. Now, of course, you won't be able to have Desmos, and we will not be doing this on the TI-84s, but what I'm showing you is basically a visualization of what's happening so that you can understand why we're doing this. T to the third minus 3t. And then I'll probably do like negative 10 to 10. Okay, it looks something like this. So you can see that I probably have a horizontal tangent line right here, and then probably one right here, and then I have a vertical tangent line probably right here somewhere. Don't know where, but this screams vertical tangent line. Where? I don't know. All right, so to figure that out, we are going to figure out what dy dt is. Now remember up in our notes that we have a horizontal tangent line whenever dy dt is equal to 0. So we're going to do dy dt, and that's going to be 3t squared minus 3, okay? And then I'm going to set this equal to 0. which means that t is equal to -1 and t is equal to 1. Now, before we plug in our coordinates, what we need to do here is verify that dxdt is not 1 and it's not -1. So what we're going to do here is also figure out dxdt and when this is 0. So 2t minus 1 is equal to 0 when t is equal to 1/2. So when t is equal to -1 and when t is equal to +1, we get a horizontal tangent line. And then when t is equal to 1/2, we get a vertical tangent line. So what does this mean? Well, that just means that if I were to plug in -1 and 1 into this, I'm going to get a point. And that's going to be a point for my horizontal tangent. And then if I were to plug in this right here, that's going to give us my vertical tangent. So if I were to actually do that and I plug in, let's say t is equal to 1, so 1 squared minus 1 plus 2, comma, 1 to the third minus 3 times 1. So that gives us 2, -2, which, plot twist, we verified that at the very beginning that that was a horizontal tangent line. Same thing with me plugging in -1. So if I plug in -1, that's going to be 1 plus 1 plus 2, -1 plus 3, and that gives us my horizontal tangent line right there. And then one more whenever we have 1/2. That's that. And we have 1/2 to the third minus 3, 1/2. And we predicted that that was a vertical tangent line there. Very cool. Oh, well, your answer should be the coordinates. So it should be the purple, the black, and the red coordinates right here. So 2, -2, 4, 2, 1.75, and -1.375. Of course, like I said, you probably will not be having the Desmos calculator. So you'll just have to plug this in and call it a day. All right, last one. We have a curve C described by the parametric equation x is equal to f of t, y is equal to g of t for all t is greater than 1. And we know that dy dt is going to be t squared plus 1 over t minus 1 times dxdt. What's the value of dy dx when t is equal to 3? All right, so to figure out what dy dx is, remember that dy dx is the same thing as dy dt over dxdt. Well, if I know that this is dy dt, I'm just going to divide by dxdt here. That means that I'm just left with t squared plus 1, t minus 1. And then using our lovely notation here, at t is equal to 3, we are going to get 9, 10 over 2, aka 5. That one was an easy one. All right. I know this was kind of a long video with 4 problems, but that was just because I just visualized 1, 2, and 3 for you guys so that you knew what was going on. But in the next video, we're going to talk about concavity with the second derivative. So we already know the first derivative, and then we're going to see what happens whenever we take the derivative of the derivative.